projects that we have ongoing, and this is stuff that I started when I was at the National Renewable Laboratory, Energy Laboratory in Golden, Colorado. And we think that this is a really completely different way to look at biofuels, and I want to sort of get very outside the box of the traditional paradigm that we think of when we think of biofuels. And I want to welcome you at any time during the talk to stop and get clarification or redirection on certain topics. I want to make sure that we try to convey the fundamentals of the biofuels as accurately as we can, and then also sort of try to open your eyes to some of the ways that we're starting to think very outside the box and how we can use biofuels. So a lot of our research effort focuses on these microalgae, and these can be found in marine environments or freshwater lakes. And these are microscopic organisms. They're going to be anywhere from about 3 to 10 to 15 microns. But under a variety of physiological conditions, they make these oil droplets, these triacylglyceride droplets, and that's a fat that's very similar to the fats that are found throughout all of the kingdoms of life. And when we accumulate these, it's thought that the majority of the fossil fuels that we currently burn today are derived from oils that were made by algal biomass that with centuries of heat and pressure and time have been created and generated into the coal and the fossil energy reserves that we have today. And our real goal now is to be able to generate these oil droplets basically as fast as we burn them within a year's time. And if we adopt and accept this paradigm that most of the fossil fuel that we burn today is of this photosynthetic algal origin, does anybody have an estimate for how many years of photosynthate we burn every year? We burn 1 million years of photosynthate every single year. And so that's an amazing pace. And so we're going to have to give this in real time. It's going to take fundamental, huge research advances. And we'll start to talk about the physics of this. And although we're highly intrigued and interested in biofuels, there's some real limitations that we can't get away from. We have to really define those very carefully and then start to talk about how we're going to overcome each one of those systematically. So this research is obviously done by a team of graduate students and postdocs, and these are the people that I have in my laboratory. I'm going to talk about several of the people that have contributed to the slides I'm going to show today, primarily Jonathan Muser and Randa Radakovitz. Both of them made key contributions to the data I'm going to show, and both of those individuals have gone on to jobs at Synthetic Genomics in San Diego, which is Craig Venter's biofuels company, that's working in collaboration with Exxon, which is just down the road here. And that collaboration goes in fits and starts, but they are both working with Craig Venter's team and have both taken over leadership positions there. And I think that we can't really have a legitimate conversation about biofuels from any source without first visiting what the fundamentals of photosynthesis are and how much biofuel we could really get from photosynthesis. What this means in terms of both economics as well as policy. And so we usually draw the photosynthesis electron transport chain in what's called the Z scheme, although it looks like an N more when you lay it out this way. But this is an energetic profile of the energy it takes to get a charged separated intermediate and electron transferred to a variety of carriers, where ultimately it comes to a redox protein called ferredoxin, and that electron can then be used in the CO2 fixation reactions. And then once CO2 has been fixed, we primarily go to lipids or starch or to proteins to make more cells. But there's a thing that you notice immediately when you look at how photosynthesis evolved in nature. And the first thing with photosynthesis is there's two photosystems. So you need to harvest 2 photons of sunlight to move 1 electron to the level of ferredoxin where it can fix CO2. And that means that we can only be 50% efficient in transforming the energy in sunlight into a fuel molecule. The second problem we face with photosynthesis is that wavelengths of light that are greater than 700 nanometers do not have enough energy to create a charged, stable, separated intermediate within the photosynthetic electron transport processes. And so the energy that's greater than 700 nanometers of light is not used by photosynthetic organisms. And half the energy in the solar spectrum is contained in that region. There's a third big inefficiency that comes from photosynthesis, and that is wavelengths of light that are less than 680 nanometers have too much energy relative to the charged, stable intermediate that's formed by the reaction centers in photosynthesis. And that excess energy has to come out primarily in the form of heat. Now, photosynthesis is an incredible thing because we can transfer electrons through these systems with near quantum unity, which means every photon that comes in is giving us a charge, separated electron event and transfer. But it does this at an energetic loss. It transfers from carrier to carrier extremely rapidly to rapidly separate the excited electron so it doesn't recombine back into the ground state. And it does this in a very thermodynamically downhill orientation, such that we spatially move that electron very fast from the reaction center. But to do that, we lose energy. Now, biology's come up with ingenious ways to recapture some of this energy, primarily in the form of making a proton gradient for ATP synthesis later. But because the wavelengths of light less than 680 have too much energy, and because of these losses in electron transfer so we can attain quantum unity, it turns out that we take another 50% hit in the efficiency of the transformation of sunlight into energy, into fixed carbon. So we can take all this up, and what does all that mean? Okay, we take three 50% losses. One because of two photosystems, one because we can't use wavelengths of light above 700 nanometers, and one because we have all these downhill reactions set up and wavelengths of light less than 680 have too much energy relative to the charge stability. That means the most efficient we can possibly be using photosynthesis is 12.5%. That means the most we can do from the energy in sunlight, transferring into a fuel, if we pencil every electron from water to fixed CO2, is 12.5%. And we operate right now from a corn perspective of biofuels at less than 1% photon conversion efficiency. It's absolutely absurd. And it's probably more energy intensive to get that fuel out than it is than you yield from it in the form of fertilizer and cultivation and management. So it might not even be energy positive in many cases, which is a real problem if we want a legitimate long-term solution. So what does that mean when we say 12.5% energy conversion efficiency from sunlight to fuel? What that means is you can take a square meter, and per square meter, at maximum photosynthetic efficiency, you'll get about 7 gallons of fuel per year. What that means is you're not going to put anything on the roof of your car that's bio-orientated unless you're going to drive your car with 21 gallons of fuel per year. How much fuel does the average car use in this country? Does anybody know? About 700 gallons a year on average is the typical number that's thrown out there. So the scales become huge. And so even at maximum photosynthetic efficiency, we're going to have to be able to come out here with a pretty big footprint to harvest solar energy so that we can power our automobiles. Now, if we go to maximum photosynthetic efficiency, we can take an acre, a square about 65 yards by 65 yards, and we can run about 40 cars. If we're going to be operating at a tenth of that, which we are now, we're going to be able to run about 4 cars. That's all going to have policy implications, and it's going to have things that we think about in terms of terrestrial landscape and light harvesting. Now, I think that that's the bad news, that we have a design that's not as efficient as we would like it to be. But as I hope we go through this, I think it's close enough where we can do very practical things. But we have to pursue a biofuel strategy that's legitimate at the cost-effective transformation of the energy and sunlight into a fuel molecule. And I want to go very deep into some of the biology and some of the things that we're thinking about in terms of how to use algae to do this, because there's some ways that I think are extremely creative. I think human ingenuity is absolutely astounding. And I think if we come at these from some perspectives that are a little bit unique, we can actually get to a legitimate solution. And we'll talk about some of the things we're looking at and thinking about. Now, in Colorado, fracking is all the latest news. I mean, we can go in, we can bust up fossil deposits, we can get a lot more oil to flow. Production is actually going to increase for the first time in ages. Nobody ever thought that was going to happen again. But if we go back to our general formula, that we can do a base calculation of how much photosynthesis happens in the oceans and around the planet, we can figure out the amount of carbon that's settled, figure out the amount of carbon that's stored as fossil fuel. We burn 1 million years of photosynthate a year. Photosynthesis emerged in the planet about 2.5 billion years ago, give or take. We can do the math on that. We can say at current consumption rates, we have 2,500 years of fossil fuel. And above that, about 10% is going to be readily harvested or extracted in an energy positive manner. If we do that, we're at about 250 years of fuel, maybe, give or take. Does anybody know when the first oil-centric well was drilled in the world, and where it was drilled? besides faculty. It was drilled in the 1860s in Pennsylvania. And it was done for a long time. They knew the oil was there, but it was a nuisance. It was a painful thing. They didn't really want to deal with it in these salt wells that they had. But then the price of oil went up, and everything was whale oil then. And that was biofuels back in the old days, was a bunch of lonely men on a ship with sharp spears chasing whales across the oceans, and then bringing them back and taking the oil out of them. And a sperm whale could have up to 4 tons of oil in its head. But as we only drilled the first oil-centric well for those purposes 150 years ago, we're already starting to talk about a decline. And we can talk about fracking giving us more production, but even if we take it on the physical basis of what we know about photosynthesis and settling, we've probably only got about 250, 300 years of current consumption rates. And although the width of this might be debatable, if we start to put up this very unique time in history in geological perspective, it's just going to be a blip. We're just going to go along and we're going to have this wonderful short period. It might be 300, it might be 500 years, where lots of fossil energy was relatively easily available and we consumed it. Now, we may not have to necessarily worry about this as much in our lifestyle, in our lifetime, because we're probably going to have access to plenty of fossil fuel. The question is you know, if this world population continues to expand, India and China consume, is that going to put a price constraint on it? Are we going to get serious about climate change? Is that going to be something that we're going to have real policy decision and lifestyle transformation on? And if we're going to do it, how are we going to enable that? And that gets back to biofuels in general. At some point, we have to have a solution. In our lifetime, the importance may be variable. But at some point, we're going to have another way to come up with food and fuel for a planet that wants to go to 9 billion people. We have 7 billion now. If we're going to go to 9 billion, we have terrestrial ecosystem degradation alterations. And everybody wants food and a high standard of living. How are we going to get that? And at some point, I think we're going to have to turn back to biology to get these products, particularly for food. But as I'm going to hopefully show today, also materials, and then ultimately fuel. So we can go and do some of these back-of-the-envelope calculations and look at where we are today. And the DOE's holy grail for algae is that you can come up with the equivalent of 5,000 gallons per acre per year. It's all about a footprint thing, how big of a piece of the planet you have to harvest, how much fuel is going to come out of this, and then how do the economics work. This has all got to be revenue positive and certainly energy positive. And I would argue many of the biofuels approaches today are not even energy positive, and so we have to dig very deep under the hood to define it. So if we look at the best alternatives, it's probably palm oil. The palm can be very hard on terrestrial ecosystems. And the actual gains you get out of there are about 1/10 of what we can get out of algae. Now this is the DOE's